combinations, and the first thing I kind of want to really highlight in here is the idea that combinations are very different from permutations, in particular in terms of um, the order not mattering. And I really want to highlight the idea of what it means for an order to matter versus an order to not matter. Let's look at one of the examples we had from the previous lesson. Was this idea of having say paintings or pictures that you wanted to hang up on the wall. So let's say you had all these paintings that you wanted to hang up on the wall. 1, 2, 3. I think there was 7 of them in the example. 4, 5, 6, and 7. Right. So we had 7 paintings that we wanted to hang up on the wall. And the idea was, with the permutation, is we had to choose 4 of them. So we had this idea with permutation of 7 items, choosing only 4 of them at a time. And the idea was, so here's our formula for that. That was 7 factorial divided by 7 minus 4 factorial. That's the formula. That's using the formula there for calculating a permutation. But the idea was that, well, the first time that we arrange these paintings on a wall, we take maybe 1, let's say 3, 4, and say 5, right? Right. So we take 1, 3, 4, and 5. Okay. And the idea was with permutations is that this is the first time we display these 4 paintings on the wall, and maybe the following day we write, okay, we don't need to replace any of these, but we want to arrange them in a different way. And so maybe we take 5 first, then we take 1, then we take 3 and 4, and what we're saying here with this 5, 1, 3, 4 is we're saying that this is a different permutation of those 4 paintings. So when you go through your 7 factorial when you go through all your 7 paintings, the first idea here was how many different combinations or how many different arrangements can you get out of 7 paintings? Well, that was 7 factorial, right? Which is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? And then we reduced it down. We said, okay, well, now we're only going to choose 4 of them at a time. So we had this reduction that went on. We did have the 7, so we divided by the difference, the factorial of the difference. And so this one here gave us 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by just 3 times 2 times 1. What we found was we were cancelling above and below, and what we were doing, reducing the number a little bit there, okay? All right, so the idea here is we only reduced the number a little bit. So this was the original number of permutations just of 7, right? Choosing 7, 7, how many different ways can we arrange 7 paintings? And how many ways can we arrange 4 of those 7 paintings at a time? That was permutations. Notice this is a repetition of those 4 paintings, 1, 3, 4, and 5. It's just in a different order, right? So permutations, we said that order matters, right? Order matters in our calculation. Right? So order matters when we're calculating that. So we look at 1, 3, 4, 5 differently than from 5, 1, 3, 4. And therefore, we of course, you different arrangements of that, 3, 4, 1, 5, and so on. The order matters in the way we're showing it. Well, combinations can be a lot more useful, because with combinations, order doesn't matter. So the idea being that is if you're taking your paintings, right, and you've displayed 1, 3, 4, and 5 together, you don't care about the order of these. You don't care which order you've placed them in, right? The next time you display a new set of paintings, it's not going to have the same paintings in it, right? You're going to choose 4 of them, but you're not going to have 1, 3, 4, and 5 all together ever again. You might have 1, 3, 4, 6, or 1, 3, 4, 7, right? Or 1, 3, 4, 2, right? So you might have 3 of them together again, but you're never going to have the same 4 together again. The idea being that you're not going to consider the 5, 1, 3, 4 as a different arrangement of paintings, right? The order does not matter. You've already shown them, done, right? So as you might imagine, this is going to reduce things quite considerably, right? And if we look at the formula here, what we're going to have here is we're going to have a 7 factorial divided by 4 factorial times 7 minus 4 factorial, right? So we just increased our denominator by a multiple of 4 factorial, which is quite amazing. When we look at this, it actually tidies things out really, really nicely. So 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Divided by, look at this, 4 times 3 times 2 times 1 times, and 7 minus 4 is 3, so that's 3 times 2 times 1. Now, what we'll always notice, right, in our cancellation is that the r factorial will always cancel out with the end of the n factorial. So this r factorial is always going to cancel out, right, with the end of the n factorial. So what we're going to end up with is we're going to end up with n minus r terms in our numerator and n minus r terms in our denominator always. So we'll have 3, the first, in this case, the first 3 of 765, or of 7 factorial, and we'll have the last 3 of the other, so 3, 2, 1. Okay, so because 7 minus 4 is 3, we're going to have 3 terms in the numerator, 3 terms in the denominator, and of course we can still do our cancelling, right? Because something like 3 times 2 is 6, and therefore we get 35. So you can see that there are far fewer combinations than there are permutations, right? When the order does not matter, there are far fewer combinations than when the order matters, and you're adding in all of those extras because the order matters. Okay, so let's look at a few more examples and help you guys get the hang of this. Okay, so how many ways can 10 students in a class be chosen for a group of 5? So what this is a combination of 10 choose 5. Combination of 10 choose 5, that is 10 factorial divided by 5 factorial times 10 minus 5 factorial. Okay, so if we write this out, let's write this one out. We won't write the other ones out when we get to it. 10, 9, 8, 7, 6 times 5 times 4 times 3 times 2 times 1 in the numerator. And then in the denominator, we have 5 times 4 times 3 times 2 times 1. And 10 minus 5 is 5, so times 5 times 4 times 3 times 2 times 1. And as we see, once again, we see the last 5 terms here in the numerator cancel out with the first 5 terms in the denominator. Okay, so that's immediately what's going to happen. And we end up with 5 terms in the numerator, 5 terms in the denominator as expected, right? And that's specifically the 10 minus 5. So when you look at n minus r, that's how many terms you will have in the numerator and how many terms you'll have left in the denominator. And then you can start canceling things out, right? So we're going to go 3 times 2 is 6. We're going to go 4 goes into 8 twice, and 5 goes into 10 twice. So we've got, we've ended up with 2 times 9 times 2 times 7. So 7 times 9 is 63, times 2 is 126, times 2 is 252. Okay, so that's how we work that one out. Pull out a calculator and check I've got my math right in that one. Okay, so we're going to tidy things up a little bit more. We're not going to rewrite this beginning and end of the beginning of the numerator, the denominator, the end of the numerator, because it's irrelevant. We don't need to. We're also going to do this calculation in line as we work our way through it. So let's see how that works out. So this one here, how many ways can 4 out of 7 books be borrowed from a library? That is a combination of 7 choose 4. So this here is 7 factorial divided by 4 factorial times 3 factorial, right? Because 7 minus 4 is equal to 3, okay? So that gives us 7 times 6 times 5. We're going to stop there because the rest is 4, 3, 2, 1. Divided by, and we should have 3 terms, 3 times 2 times 1, okay? Right? So having it here is useful. So now we've got the 3 and the 2 cancel out with the 6, and we get 35 different ways. Right? Another example here, combination of 6 choose 3. Okay, is 6 factorial times 3 factorial, and 6 minus 3 is 3 factorial. We're going to have 3 terms. So we're going to go with 6, 5, 4, those 3 terms, and then we're going to have 3, 2, 1 from the n minus r there. So once again, 3, 2 cancels out with the 6, 5 times 4 is 20. So we've got 20 different ways of awarding 3 awards to 6 students. Okay, so we're getting the hang of this now quite quickly. Let's take a look at a few other examples here. This one here is going to be 8 factorial. 8 factorial divided by 6 factorial, and then 8 minus 6 is 2 factorial times 2 factorial. So that one there, you'll see is 8 times 7 and 2 times 1. Okay, so well, we can do a nice little cancellation right there, and that gives us 28. Right? Again, if I'm going too fast, feel free to pause and wrap your head around this. I got quite a bit to cover here. So this next one here is going to be 6 factorial divided by 5 factorial times 6 minus 5 is 1 factorial. And interestingly, that means, okay, we're going to have one term in our numerator and one term in our denominator. So one term is going to be just our 6. The 5, 4, 3, 2, 1 is getting cancelled out. And divided by 1 factorial, no need to do that. So our answer is just 6. Okay. This one here is a little bit longer. Let's take a look. So this is 11 factorial divided by 2 factorial times 11 minus 2 is 9 factorial. So we're going to have 9 terms. So let's work through that. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. And that's going to be divided by, here by 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, you're still going to have a bunch of cancellation that you can do, but it's important that you actually do it this way so that you can see which cancellations are going to occur. So even when you have widespread difference between between n and r, it's still going to tidy up for you very nicely. So this 9876 all the way down to 3 cancels out, and we get ourselves a nice easy problem. That's just 11 times 5 is 55. Okay, so there in a nutshell is what combinations are. I'm going to look at a couple of examples right down the bottom here to show you how to discern between the two, permutations and combinations. So let's take a look. Permutations, order matters. Combinations, order does not matter. So in our examples here, we're being asked to find out, well, permutation or combination first, then calculate the number of possibilities. So I'm just going to deal with permutation or combination based on these. So, dessert cart in a restaurant, customers are allowed to pick 3 desserts from the 10 that are displayed. How many ways can the desserts be selected? I don't like the last sentence there, in how many ways can the desserts be selected, because it does suggest that this is a permutation. However, this can't be a permutation because, you know, if you choose, say, an apple crumble, a peach cobbler, and an ice cream, That's the same as choosing an ice cream, a peach cobbler, and an apple crumble. Right? You're choosing food. There is no permutations here. You're choosing the same thing, and the order does not really the order does not really matter in this case, right? So that's really the idea, is decide whether order matters or order does not matter. In this case, order does not matter in this case. Order does not matter in this case, so this is going to be a combination. Right? Because you don't care which order you're getting those three desserts in. Once you get those three desserts, you're going to want a different set of desserts. Okay. In the other hand, choosing a president versus a vice president, well, I'm pretty sure that somebody who's been a president before, or especially somebody who's been a vice president before, is going to want to be a president next, right? And he's going to be okay with having his previous president as a running mate, as a vice president, right? So you could have a presidency and a vice presidency, and then the next term round flip it around and have the vice president as the president and the president as the vice president. So in this case here, order does not matter. They want as many different permutations as possible. So this here would be a permutation. In particular, order matters. So president first, vice president second is different from vice president first, president second. It's really the person, right? If you were to look at say previous presidencies, stick away from politics. If you were to look at Obama and Biden, and let's say this time around Biden chose Obama as his running mate, that is different from Biden, Obama, right? Right. So the order does matter. Okay. So what we're going to look at here is we're going to look at the calculation. All right. So the combination here, this is so the combination. Just remind yourself here, the combination of from 10 items, we're going to choose 3 is equal to those 10 items, 10 factorial, divided by 3 factorial, times 10 minus 3, which is 7 factorial. Right, that's the combination, and that's going to be 10 times 9 times 8 times 7 times 6 times 5 times 4, divided by 7 times 6 times 5 times 4 times 3 times 2 times 1, and as you can see, we have some nice cancellations occurring here. 7654 cancels out with the 7654. 3 will go into 9 3 times, and 2 will go into 8 4 times. And so we've got 3 times 4 is 12, times 10 is 120. Right? This one here is a permutation, so permutation from 14, we're going to choose 2. And the permutation formula, that's going to be 14 factorial divided by just simply the 14 minus 2, which is 12 factorial. Right? So the difference here, we have a minus, and we're multiplying the denominator again. So 14. So this one here is even easier because this is just 14 times 13. That's 182. And I'm going to leave it at that. If you've got any questions, please feel free to ask.